record. Okay. All right. So there's a lot of boring stuff to this. All right. I did say, and this is important, right? So there's a couple of important signals in our problems, right? So sines and cosines, we've talked about those a lot, right? They come in a lot of applications, power, audio, communications. So, cell phones, all of that, where you have some sort of sinusoidal signal. And again, I use the term sinusoid to mean a cosine, right? And what is this? I guess the other thing is when I say sines and cosines, what am I referring to? Well, something that goes up and down, right? But what can we, hopefully you remember this, what can I relate sines and cosines to? Always. What's that? Complex numbers, right? So that means somehow I have some e to the j omega t plus some e to the negative j omega t somehow relates into sine and cosine. All right, well, we're going to talk more about that as we get into our next topic beginning Wednesday, which is additive combinations of sine and cosine. Those additive combinations are what we refer to typically using this term called a Fourier series. All right. So even if I have something like a square wave, or if you guys have done anything with like Raspberry Pis and robotics and stuff like that, you deal with things called pulse width modulation, right? PWM. All right. That's really kind of a Fourier series type of problem. All right. So we're going to study that beginning on Wednesday. So we talked about this idea of a unit step. All right. I introduced that when we did differential equations. A unit step. What's that? I called that U of t. Right, here's t. What did the unit step look like?
Back to like a switch.
Yeah, so before 0, it's 0, and then at 0, it becomes 1. So what I said is if I got something like this, I've got a power supply, let's say, and I close a switch at t equal to 0. If this was 1 volt, then I would call this output here U of t, right? So it models what a switch does. All right, it's a mathematical model for that. Again, not the most exciting thing in the world, but it's important, right? Then the other thing I talked about last time was this idea of an impulse or a Dirac delta, right? Which models things that happens over extremely short periods, which is a useful thing to have. All right, so we're going to talk more about that again, kind of review that. All right, and then we talked about this a little bit right before the break, signal manipulation. All right, so when we have these things with signals, there's basic things that we might do to them. So shifting, reversal, scaling, and then I can take these sort of basic building blocks here and I can combine them in different ways to make different signals. All right. Like I said, this is things that in a lot of ways you kind of seen some of it before. All right. We're just going to formalize it a little bit and I'm going to move on from it pretty quickly because I find it to be pretty boring, which I've probably said a lot now, but it is. Okay. All right. Now the stuff we'll start Wednesday is good stuff, Fourier series, which is a pretty important and powerful tool for us. Okay. All right. So time shifting. If I have one function that I shift to become another function. All right. So what I have here, f of t minus t naught. Okay. So if I take a signal and I say f of t minus t naught, if I have a negative like this, what does it mean? If I have a negative t naught's some constant here. What is g of t? Is it shifted forward or backward? Or maybe backward? You think of it. Okay, everybody says backward. Okay, let's see. So let's take that u of t, right? So here's u of t. Like that. All right. Let's say I had u of t minus 1. How would that relate to u of t? U of t and u of t minus 1, how would they relate to each other? How could I check if I didn't know? You could guess. The guess that you have probably is, well, it either starts at -1 or it starts at 1, right? How could I check? Well, plug in t equal to 0, right? If I plug in t equal to 0 into, so the way to think about this, so let's say g of t is u of t minus 1. Okay, so let's check this. So I'll make a little table here. T, G of T, U of T. Like that, okay? So if I plug in -1, okay, that's G of -1, and that would be U of what? If G of T is U of T -1, then this would be U of what value? -2, all right? So what is that? It's 0, right? If I put in 0, G of 0 is U of what? -1, which is 0. So if I plug in 1, well, that's G of 1. So G of 1 is U of 0 or 1. Okay. So if I were to plot this, right? So G of -1 was 0. G of 0 was 0. G of 1 is 1. So which way did the function move? Shifted to the right, right? So this guy would be my G of T, right? So the way I look at this here, so this is 1 right here. The way I look at this is I say, if in this particular case, if T naught is, and I don't like this. I'm gonna write it like this: T plus T naught. All right. If T naught is greater than 0 or less than 0, right? T naught's greater than 0 here in this guy goes to the left. If it's less than 0, it goes to the right. Okay. And the way that I kind of think about this is this is a signal when it's pulled to the right, meaning it's pulled, okay, so it was pulled this way. This is a delayed signal. And this is a delay, and this is an advance. So what does that mean to say that it's an advanced versus delayed? Why would I say that the function G of T here, why would I say that this is a delayed version of the one up top? Why would I say it's delayed?
Because the signal is started after
Yeah.
the original thing has been started.
Yep, it starts after the original one started. In this case, at T equal to 1 is when this thing starts. So it's delayed, right? Instead of happening at T equal to 0, it happens at T equal to 1 second. And if I had pulled it the other direction, pulled it to the left, right, then it would have started earlier. Would have started at T equal to -1, right? So that's what I would call an advance, happened beforehand. Okay. So this was one that we looked at in right before spring break here when I said, okay, let's say I've got this guy sine cubed of 2 pi 100 t. That is this. This is my f of t. So this dashed waveform that I have there, it's my f of t. All right. The signal that I have G of t here that I've shown on the screen. What would you say? Was this guy advanced or delayed? Well, technically, you could kind of think of it either way, I guess, right? If I looked at the peak here, it looks like I pulled the peak and went to there, right? Pulled that peak forward by some amount, right? So if I pulled it forward like that, what would that, how would I express that? Would that be f of,
It's gonna be delayed from the original function.
yeah.
Like
And so, yeah, so in this case, yeah, minus whatever that T naught is in this particular case, right? So in this case, it looks like that delay, if I look at it carefully, this T naught here is 0.003. So it's delayed by 3 milliseconds. How would I write that? If it's delayed by 3 milliseconds, how would I write this? F of T was this guy. So G of T is what? So it's sine cubed. And how would I write that argument here? And this is a pretty common thing, right? If I got a sinusoidal signal, right? We have shifts all the time with sinusoidal signals. You see this in circuits, right? In circuits, we said, okay, if I have a voltage that's a sine wave that goes into a circuit, coming out of that circuit, it might get bigger or smaller and get shifted left or right. So there was a phase shift. A phase shift is basically a time delay or a time advance. Okay. So how would I write that here for this guy? If this shift is 0.003, yeah, so how would you write it? So 2 pi 100 t minus 0.003 like that? Yeah, yep. Okay, this guy would be written as t minus 0.003, right? And the way to check that is if I look at this, if I plugged in t equal to 0.003, right, I should get the same value that I would have gotten for f of t, right? So if I plug in t equal to 0.003 for this, what do I get? Well, if I plug in that value at t equal to 0.003, g of 0.003 is equal to f of 0. That better be the case, right? Because it was shifted by 0.003. The only way that's going to work is if I have those parentheses there like that, right? So the way you think about that is 2 pi 100. I said 2 pi 100 times 0.003. What units would that have? What is that? 2 pi 100, what units should that have? Radians per second. And t should have units of seconds. This guy is an angle, right? This guy is in radians. So it better be an angle shift because the argument of sine is always an angle, right? So I'm shifting it by an angle.
I have a question here.
Yeah.
Yeah, like how come like the G for 0.003 is gonna be equal the same f for 0.003 because f of 0.003 is not equal 0.
It doesn't, right? So you're saying g of 0.003 equals f of 0.
Yes.
Right. So if I look at that, so g of 0.003 is here, f of 0 is here. The value there is the same for those two things.
Oh, okay. I just get
Right.
confused from. I'm sorry.
Yeah, it's tricky, right? So I mean, basically the way to look at this is plug in t equal to 0.003 in this expression. And what I'm going to get is 0.003 minus 0.003 or 0, which is the same as plugging in 0 here.
Gotcha. Thank you.
Yep. Okay. Really what you'll probably learn out of this whole thing is that, well, when I look at this T naught, if it's greater than 0, I pull it to the left. If it's less than 0, pull it to the right. Okay. The tricky part is when you have something like this, when you got sort of a factor like that, like an omega, right? That makes it a little bit tricky. All right. So what about this one here? So it's pulled by the same amount. There's a 0.003 shift. All right. So that g of t, so f of t was 2 pi sine cubed of 2 pi t, 2 pi 100 t, sorry. All right. So what is g of t here based on this arrangement? So it's a 0.003 shift. Is it left or right? It went left. So what does that mean here? So that means this guy is sine cubed of what? How would I write this one? How would I write this one? Yep, 2 pi 100 t. And this guy, this would be a plus because he's pulled to the left, right? So this is an advance. When it's an advance, you add time, you add to the argument, right? You want it to happen earlier, right? So again, it's something you get used to. It's not particularly hard. Just got to get used to it. Okay. All right. All right. Now I'm gonna come back to this time reversal thing here a little bit later. But now that I have this time shifting, I want to use this in some of my examples here. All right. So last time I talked about a new kind of function, this idea of an impulse function, which tries to model sort of something that happens very, very rapidly. All right, something that happens very fast. So the name for this guy, a Dirac delta. In math, they often call it a Dirac, named after the person that kind of first started talking about it, right? It's sometimes the term that I use most commonly is that this is the impulse, and we write it as the little delta. All right, so the little Greek letter delta. And you know, it's not a real thing, but it's sort of an idealization of something that can happen very quickly. All right, so what we say, the way I think about this is if I have a signal that is, you know, the example I guess I gave last time was I said, okay, I had a picture of a baseball player hitting a ball, right? There's a very short period of time that there is contact between the ball and the bat, right? And so for that very short period of time, you're basically putting energy into the ball to flip its direction, right? So the thing I think of is I'm applying a lot of force for a short time. So the way we think about this is I can think of that force applied to the bat as being a high value for a short time. And what we say about this is I look at this little block right here, right? So we model this delta of t, all right? We say that this thing has an area, all right? It's really high and it's really narrow. And if I look at this particular thing right here, right? If I take the limit as epsilon goes to 0, right? Well, and the limit as epsilon goes to, well, not, it's the limit as epsilon goes to infinity, right? So in other words, this guy gets really high. This guy's going to get increasingly narrow. What's going to happen to the area there? What's the limit? So area, the area A of that box. What's the area of that box? Well, how do I calculate area? Length times, yeah, length times width. So in this case, epsilon times 1 over epsilon is 1, right? So basically what we say is, so we'll let the height get really, really big and the area still 1, right? So the definition we kind of use with this thing is this guy sits, all right? The impulse sits at t equal to 0 like this. And we give it the definition that the area under the curve is 1. All right. The area under that curve is 1. All right. And we integrate from negative infinity to positive infinity. The only thing underneath that thing is 1. Okay. All right.
This
So
is the same idea for Riemann summation.
Riemann summation is basically how we kind of get to the definition of an integral, right? And with that, they talk about little boxes, right?
Okay.
It's a slightly different thing. We'll actually talk about that in terms of project 2, where we'll do a little bit of numeric integration. You did numeric derivatives, and you'll end up doing numeric integrals in project 2. So similar concept, yeah. All right. So the other thing we sort of talked about is we said, all right, so we can use this thing to pull off values at a particular function, right? So what I said is here, so if I have if I take f of t and I multiply it by delta of t, taking some function and multiplying it by delta of t has no meaning. All right, in other words, this is not equal to f of 0, right? If I multiply delta of t has no value, okay? In other words, this function has no height. It's approaching infinitely large, but it's not. All right, it's not a real thing. It has an area. Now if I say to you f of t times delta of t, this is not true. All right, what is true is I say if I integrate over a period, or not over a period, but if I integrate over some width. So the way I've defined this here is if I had a function f of t, here's f of t, and here's delta of t. If this is A and this is B, if I took f of t times delta of t and integrated over that area, then I would get the value of the function f at t equal to 0. Sometimes what I call this is the sifting property. Okay. And basically what it does is it says if I take an impulse and multiply it by something and then integrate, I sift out the value of the function at that point. All right. That actually kind of mimics what an analog to digital converter does. So we talked about, how these things model things that happen in the real world. You'll talk about this. Actually, we'll talk about this a little bit more towards the very, very end of the semester. This kind of models what, like I said, what a function generator is going to do, or not a function generator, but an ADC is going to do. All right, it sifts out or pulls values of some other underlying function. Like f of t could be an audio signal, right? That's being passed into that analog to digital converter. And the impulses and what they're doing is like sifting the values off of that waveform so that I can spit that into my digital recorder. Okay. So important thing here is delta of t is 0 for any values that are not at 0. It isn't really defined at t equal to 0. All right. It isn't really defined at those values. Okay. What we say is that its area is defined. If I look at the integral, and as long as here, right? So here's delta of t. Right. So delta of t is here. If a and b look like that, then this integral is 1. But if I had this picture here where delta of t is there and a is here and b is here, this integral is equal to 0. Okay, because I'm not integrating over an area that includes it. Right. Again, not particularly surprising. Right. That's a kind of just basics of calculus right there. Okay. All right. So let's look at a couple of different examples here. So if I said, oh man, I lost I'll cover these up. I had little boxes over them. They disappeared. It's not going to work. All right. So if I look at these here, if I say, all right, so if I integrate from 0 plus, first of all, I use that in talking about differential equation and circuit stuff all the time. If I say 0 plus, where is 0 plus? Yeah, it's a little bit to the right of 0. So if I say I'm integrating from 0 plus to 1 on delta of t, what's the area under that curve? From 0 plus to 1. So 0 plus would be like right over here to 1. What's the area there? 0. Okay. Let's say from 0 minus, right? 0 minus to 1. Where's 0 minus? That would be over here, right? So this is 0 minus, and here's 1 over here. What's the area there? 1. Okay. Now let's say from -1 to 0 minus. Let's say that's right here. All right. So -1 would be over here. What did I do? Wow, that's crazy. All right. So -1 is here. 0 minus is right there. What's that area? 0. All right. And then if I was doing from -1, so -1 is here, 0 plus would be over here. What's that area? 1. All right. So I just got to be careful about what I include in my limits right there. Okay. Again, not the most exciting thing. All right. Now, I can scale these things. All right. If I scale an impulse, all right, by multiplying it by some factor, then it looks like when we draw the arrow that it's twice as large. Did it actually become twice as large? What was the height of an impulse? Undefined, right? It's infinitely large, so it didn't become 2 times infinitely large. That doesn't mean anything. What happened? What really changed there with this thing? By multiplying by 2, if I had 2, so if I said I had 2 delta of t, right? I didn't change its height by a factor of 2, but I changed its what? The integral will be 2. I changed the area under the curve, right? So the area of this guy would now be 2. All right. It's not that it's twice as large, but the area under the curve is twice as large. Okay. We don't have a good way to show that, so we just show the number 2 next to the arrow. And if I had, let's say, 2 of these on my graph, usually I show it as twice as high. Okay. But again, it has no meaning to say that it's a unit 2 high, right? Because again, the value of an impulse is effectively infinite. You're saying it's something that's really, really large, but really, really narrow. Okay. So the other thing is here, if I talk about shifting, right? Delta of t minus 1. Where would delta of t minus 1 be? How would I show that? Where would that be? Is that to the left or the right? To the right. Okay, so delta t minus 1 would be to say this guy is now located at 1. All right. Again, not particularly exciting, but it is an important fact that we need, right? So what this kind of leads to is, again, kind of furthering this idea of what I call the sifting property. So if I take this signal f of t and I multiply it by something that's been shifted by t, okay, then what I do is I pull off the value here at this t equal to capital T. All right, but I got to take the integral. All right, and again, the integral has to include obviously the value of t. So t has to be somewhere between those limits. Okay, so let's look at some examples here. All right, so let's say I've got this guy here. F of t is this integral from -3 to 2. All right, integral of f of t times this whole thing. All right, so let's first of all, let's draw out just this function right here, right, that includes these impulses, 2 plus all that stuff. What would that look like? All right, so versus time like that. So 2 plus delta of t plus 1 minus 3 times delta of t minus 1 plus 2 times delta t plus 3. All right. Well, 2 is easy, right? 2 would just be, it would go along like that, right? At a height 2. I think I want to shift that a little bit higher, give myself some more space. All right. Now, how would I draw in these impulses here? Delta of t plus 1, where would that be sitting? -1. All right, so that I'd have, here's at -1, that I'd have something that's a unit. I draw it a unit 1 high. Then -3 times delta of t minus 1. What would that look like? Yep, it'd be at time 1, and its height would, I draw it down here. I show that arrow having a height 3 times bigger than the other one. Again, its height's not actually bigger, its area is bigger, right? But it's really hard to show that that it's shrinking, right? So we have to show that it's getting bigger. We need some way to graphically represent it. So we show it that way, even though it didn't actually get that way. All right. Then I have this 2 times delta of t plus 3. Where do I show that guy? Where's he sitting? -3. So here's -2. Here's -3. All right. And his height would be how big? 2. All right. And again, not that his height actually is bigger, his area, right? Okay. So if I calculated this thing right here, so let's say my f of t was some function, I don't know, let's say this is f of t right here, some function, yeah? And I'm integrating from -2, so that would be from here to, so there's 2, here's 3. All right, I'm integrating between these boundaries right there. -2 to 3, okay? What would I say is the output of that integral? Well, I have, first of all, I have the number 2 times f of t. So the first result here is I'd have 2 times whatever that integral is, right? Whatever that is, that's what this part gives me, right? What about when I have delta of t plus 1 times f of t? What do I get from this guy right here? What does that give me? When I multiply delta of t plus 1 by f of t and then integrate over this range, what does this guy do for me?
Is
So
it a constant who will get out of the integration?
Yeah, so what's the constant that I'll get out?
The minus one?
I would get the value of that function at minus 1. Right, so I would get the value of the function f of minus 1. Okay, what would I get from this right here? What would I get from that guy? The next impulse. So there's an impulse. Let's just track the impulses we move through, right? So this impulse here picks off the value of the function f of t at t equal to minus 1. This impulse right here is going to pick off the value of the function right here. Okay, so what's that going to give me? What would I write that as? So this guy would give me what?
As a 1?
It would give me 3, or specifically minus 3, right? Minus 3 times the value of the function at 1. Okay, right? Now, do I include this guy, his effect here? No, why not? It's outside the bounds of the integration. Okay, it's outside the bounds of the integration, right? So this is the result of this kind of sifting property. And like I said, if I was sampling a function, right, what I would probably do then to sample that function is I would take that function and I would think of multiplying it by sort of a series of impulses at sort of fixed time steps. Okay, so like in project 2, I gave you those audio files that were sampled at a particular rate, right? What that means is the sampling process means that you took some actual sound and that sound was recorded. You took values out of that sound at fixed times and sent them into a digital file. The act of doing that can be basically modeled as multiplying the original signal by these impulses and integrate. All right, that mathematical process is really important for us to think about what's happening when we start processing those audio signals. All right, so we're going to start dealing with that kind of thinking here. You're going to deal with that a lot when you get into signals and systems. All right, so we're trying to get the basic kind of building blocks, I guess, if you will, of trying to think about those problems. But then we'll deal with that a little bit more when we get into some of the Fourier series stuff. All right. Okay. The other important thing is this impulse is effectively the derivative of the unit step. Okay. And the way I kind of think about this, if I look at if I had a ramp function like this, so you normally think about it and say, well, if I have something that changes quickly over a short period of time, you should be able to say, well, the derivative of this function here would be 0 before 0. This guy's linear right here, and then he levels off, right? So you should be able to look at this and say, well, the derivative is the slope, right? So if I look at this, this guy has a really high slope when he's changing like this. Well, if I took this slope and I increased it, in other words, I tried to make this ramp happen shorter over a shorter period of time, what would happen to the height of this thing? If I pulled this shorter, if I pulled t smaller, so let's say t moved that way, what would happen to the height of this thing? Well, this guy would grow, okay? Until eventually this guy basically was 0 width, so this guy would be infinite height, okay? All right, so in the limit, as t really does go to 0, what we say here is I have the step function or the unit step, right? The derivative of that is the impulse, okay? So delta of t is the derivative of that. Now, where is that useful? That's useful in a lot of places, right? The example I gave last time is I said, well, let's say I had an inductor that was at t equal to 0. He was powering something, some load, and then at t equal to 0, I opened a switch up, right? When I open that switch up, I get some kind of a, what's going to happen? What would the current look like in this circuit? So I of t, what would I of t look like? The current in that circuit. Let's say this is I of t. And at t equal to 0, I open that switch. And let's say this was a DC source. Let's say this was 1 volt and this is 1 ohm. What would the current be in that circuit? So switch was closed for a long time before t equal to 0. How much current would be in there before t equal to 0? 1 amp. All right.
Oh, yep.
Yeah. And then it would drop to 0. What would the voltage across the inductor look like?
Can you repeat the question one more time?
What would the voltage across the inductor look like? If this was the current, what would the voltage across the inductor look like?
It's not gonna drop because it's gonna be act like a short circuit.
Okay, well, at t equal to 0, right? So before t equal to 0, the voltage was 0. Because an inductor, if a current's been going through an inductor for a long time, it's a short circuit, right? In steady state, inductor looks like a short circuit with DC circuits. At t equal to 0, I open that switch up. What's the voltage gonna look like? Well, what's the relationship there? V L equal, how does V on the inductor relate to the current in the inductor?
The ergo for the inductor.
L di dt, right? So what would the voltage be if the current was 1 amp and then suddenly became 0? It would be a negative impulse, be a negative delta of t right there, right? So what does that mean physically? What would the voltage look like? For a really short period of time, that voltage would be what? Stupid high, right? It would be nearly infinity, right? The fact that I have a voltage that's nearly infinite means if I did a KVL around this loop, the voltage across that switch would get really, really big too. A voltage really, really big across that switch. If I get a really big voltage across like air, say I have a capacitor and I put a big voltage across it. What happens if I put a big voltage across? I get dielectric breakdown, but I get arcing, right? So you've done this if you've ever pulled take a hair dryer as the classic example, right? I had a hair dryer plugged into the wall and then just yanked the cord out all of a sudden. What happens? You see an arc of some kind, right? Basically, that's the result of taking a current and forcing it to 0, and there's this LDI/dt that's happening that's causing this huge voltage spike. That big voltage spike causes basically what we call arcing. It breaks down the dielectric in the air, okay? All right, it's a useful way of thinking about stuff. Is it really infinitely large? No. Is it really big? Yeah, it is really big, right? The di/dt here is never, like in other words, right here at this particular point in time, di/dt is never infinite. It might be 10 to the 9th or 10 to the 10th. It might be a really big number, but it's not ever going to be infinite. All right, but it will be really big, okay? Depending on how you're pulling that thing. All right, so let's say I had something like this. So in calculus, you would have stayed away from this. Calculus, you would have looked at this and you would have, so let's say I want to take the derivative of this. What would you have said about the derivative at these points? You would have said undefined. All right, in a more generalized context, we say, no, they're not undefined. We define them by the Dirac delta, by the impulse. All right, we need some way of representing those things. So and the reason why is I need some way of thinking about a problem like this. Right. In reality, I can't, so this is modeling the idea of what I do if I just yank that cord out of the wall while there's current running. Right. That's not something that, really happens in 0 time, but I need a way of modeling it. And so the impulse gives me a way to do that. And I need that capability to be able to handle this sort of problem. So let's say I wanted to draw the derivative of this thing. Right. So I have f of t here, and I want to look at d/dt of f of t. What would that look like? From 0 to 1, what would it be? Be 1, right? This guy's basically rising by 1 in a time 1. So this guy's going to have a slope of 1. All right, then what do I get there at this point? Well, this guy effectively comes down, and I say at this point, it's represented by an impulse, right? This guy would be represented by an impulse right here, okay? And then what about this area right here? From 1 to 2, it's like that, right? What would I say? How would I represent the derivative right here? It would be an impulse that would be negative, and it would go down by 2. All right, because clearly it's got to have twice the rate there, right? So this guy would go to 0, and this would be drawn as coming down -2, because I went down twice as much as I did there. Okay, and then that's kind of an unclear thought. It's going to start on the x-axis. There is where I would show that happening. All right. And then the rest of the time, this guy has a slope of 1 again, right? This is sort of a weird way of kind of thinking about this sort of thing. I mean, normally in the context that we think about this, we think of it as kind of a unit step, in which case I would think of that as coming up right there and having that value. Okay. Typically you see something more like that. All right. All right. All right. So signal manipulation stuff we talked about. I think I moved one of my slides there at the beginning. So there's not a whole lot of other stuff we can talk about the delta of t. All right. It's an important function. We're going to use it. We're going to use it a lot when we get into the Fourier stuff. Okay. That's why I wanted to introduce it before we got into Fourier, because it helps us, right? In particular, one of the ways that it helps us is we're going to show a lot of stuff when we get into Fourier, where I want to look at a particular signal as a function of frequency. So I want to look at some signal that I measure in the real world, and I want to say, well, at what frequencies are there information? If I had a sine wave, that sine wave has information at only one frequency. So that impulse gives me a way to capture that and say, well, I only have something at that one point. All right. So we're going to make more sense of that concept later on. All right. But that's one of the reasons I use this, is that it helps to represent something that happens at only one particular point. Okay. All right. So we talked about time shifting. There is also the idea of time reversal. I got my slides in the wrong order here, so I'll come back to this. This was my f of t, where my f of t was this guy, sine cubed of 2 pi 100t. Let's say I do a time reversal, right? So I look at f of minus t. What would f of minus t look like? Well, yeah, so I'd put a negative in here, right, into the argument here. What would that do to the way this function looks? Reflected across the y-axis, right? So something that's happening here at this particular point would be happening at the exact opposite point. Okay. So I see here's t equal to 0. So this is my y-axis effectively right here. Okay. At that point. So I would take this point and move it to the exact opposite point on the other side. So I would get, when I post these, I'll put them in the right order. I'd get this. All right. So what was over here has moved to over here. All right. So it's a flip. So this guy is a flip across. So I say a flip. Better term is probably a reflection across the y-axis. Okay. All right. Then we can talk about time scaling. Okay. So when I take a function, some basic function f, and I multiply time by some constant, okay, to get a new function. All right. So let's take an example. Let's say I want to take this function right here. This is my original f of t, and I have g of t equal to f of 3t. Okay. So what I want to do is I want to figure out here what's going to happen? So at t equal to 2, I would be computing g of 2, and that would be f of 6. Okay. So what does that equal to? Based on this picture that I drew right here, this is my f of t. What does that equal to? Where's 6? Well, 6 is all the way down here somewhere. What is that? Based on this picture, it should be equal to what? 0, right? So g of 1 is f of what, according to this? F of 3. Well, that looks like it's also 0. So then I said, well, t equal to 1/3. So g of 1/3 is equal to f of 3 times 1/3. 3 times f of 3 times 1/3 would be f of 1. What's that look like it is here? Should probably be careful. It may not be all that clearly defined there, but what does that look like it's about to transition to? From 0 to what? 1. Okay. So what does it look like I'm doing here? What's it look like I'm doing? By multiplying time by 3, what am I changing? Am I expanding this thing or am I shrinking it? I'm shrinking it, right? I'm pushing it in, right? So t equal to 0, g of 0 would be f of 0. So that's still equal to 1. So at t equal to minus 1/3, I'd have g of minus 1/3 is f of 3 times minus 1/3. That's equal to f of minus 1, which looks like it's 1. If I plugged in something like t equal to minus 1, I would get g of minus 1 equals f of minus 3, which is 0. Okay. So what I did was I took this guy. So if this was f of t, g of t is now going from minus 1/3 to 1/3. So I shrunk it. Okay. So what I see here is if a is less than 0 or a is greater than 0, if a is greater than 0, this is a shrinking. I guess let me see, I compact it. This is an expansion. All right. So if I had said to you, well, what would happen if I looked at f of 1/3 t? What would f of 1/3 t look like? How would I draw f of 1/3 t? So if I had g of t equal to that, what would that look like? Yep, step would start at -3 and it would go to 3 like that, right? -3 to 3 and its height would be 1, right? So this guy is an expansion, right? Whereas this one was a compaction, okay? Again, not the most sort of exciting thing in the world, all right? All right, now let's look at this guy here. So this is a pulse, right? So I wrote this guy, I gave him a name here, P of t, all right? So a pulse is something that I usually use to, different than an impulse. An impulse is something that's basically infinitesimally small and infinitely high, right? This guy is a pulse, meaning he rises up for a short period of time. Very common thing in digital circuits, right? I have a pulse that is read in by a microcontroller, right? That signals something to a microcontroller to do something, right? Okay. All right, this is a pulse. This guy can be thought of as kind of related to that unit step, right? What did the unit step look like? Right, if I had u of t, how do we define the unit step? 0 before t equal to 0, then he rises up and he stays that way for a while. Okay. All right. So I could relate this somehow to the unit step. So here's u of t. So u of t becomes 1 at t equal to 0. what other signal could I use to create something like this? If let's say I wanted to add another signal to this guy. Let's say I wanted to add, oh, it does that. Here we go. Huh, got super slow there. All right, let's say I want to add another signal to U of t to make this. What would I have to add to it? What would I want to do? Well, U of t becomes 1 for all values of t after t equal to 0, right? So what would I have to add to that to create this thing over here? Yeah, of a negative U of t. So, and where would it have to start? T, yeah, t equal to 3. So here's 3. Let's say I had this, right? If I had a signal, if I had a unit step that was shifted to start at t equal to 3 and had a height of -1, if I took these two things and added them together, then I would get this result, right? The way I think about this is I add at each point in time, I add these two signals together. So at t equal to 0, I'm saying I have 1 plus 0. At t equal to 1, right here, I have 1 plus 0. At t equal to 2, right, I have 1 plus 0. At t equal to 3, I have 1 minus 1. At t equal to 4, I have 1 minus 1 is 0. So I can say that these two guys together give me this. So how would I write that? I'd say it's U of t. And then how would I express this guy down here? Negative, not negative U of t, that's close, right? Negative U of what? T minus 3, right? So U of t minus U of t minus 3. That is this guy here, P of t. P of t is a combination of those two signals. Okay. All right. That's a common way that we try to represent those things. All right. Now, what we're going to start dealing with is things like if I have a clock signal in digital, right? A clock signal is sort of a series of pulses, right? A clock signal is a square wave. It's something that goes 0, 1, 0, 1, 0, 1, 0, 1. That's best thought of as a sum of sine waves, which is what we'll see beginning on Wednesday. Okay, and that's what gets us into this concept of the Fourier series. All right. So that's all I really want to kind of talk about today. I'm going to end it a little bit early to give you guys an opportunity here to ask any questions that you want to ask me about the project. I had a bunch of you guys that responded to my note in Discord about the Smart Grid Lab. I haven't had a chance to reply to everybody that sent me something, but if you wanted to ask me any questions about that, you can come down and ask, or if you ask about the project, come and ask about that. All right. That's all I got. And then, yeah, office hours are this